Okay, so we have the negative end on the capacitor and the positive end on the other side of the resistor. So we've got a capacitor and a resistor in series. The scope ground is right here. The yellow probe is right there. It's measuring the voltage across the capacitor. The blue probe is measuring the voltage across the entire circuit from here to here. And I've got the scope set up for a 6 volts peak to peak. So the blue one is the circuit voltage. It's 6 volts peak to peak. Now, the DC offset on this, you want to make sure when you do this that your scope is evenly distributed between across this line, so it goes up as far as it goes down. And right now it is not, so you can use the DC offset on your function generator to bring that back up to where it should be. So I've got 1, 2, 3 divisions up and 1, 2, 3 divisions down. The other waveform should just follow it and be equidistant between here and here. You want to set both your grounds here. You want to set both your grounds right in the middle. And I have these set for the blue one is 1 volt per division and the yellow one is 1 volt per division right here. So they're on the same scale, which is kind of nice to see. The blue one, I've got this set up for peak-to-peak voltage and peak-to-peak voltage. So I got 6 volts from here to here. And for the peak-to-peak, and this one is measuring the cap voltage. This is the yellow one. We're measuring the cap voltage from here to here. Okay. And we said it would be just a hair over 5 volts. And this is showing us 4.96 volts. Peak to peak there. Okay. Next thing we need to do is to measure this phase here. Now, I'm setting on 1 kilohertz here, almost exactly, 998.19 hertz, so I'm really close. So I've got a 1 millisecond from where the waveform starts to where it starts over, 1 millisecond. What we're going to do is measure this phase shift here between that one and this one. Something you want to notice is that the circuit voltage here is ahead of the voltage across the cap. Okay, remember cap had a negative 90-degree voltage on it. So I've got this circuit voltage is ahead of that, and what I'm going to do is stretch this out a little bit right there. And this does not work unless you've got this set up so that that's as high as that is low. And I'm going to hit the cursors and run this cursor over to where that 0 crossing is. And cursor 2, and set it here to the 0 crossing. There we go, right at the 0 crossing. And that thing is at 90 microseconds. Okay, so what I want to do is a little bit of math now, find out how many degrees 90 microseconds is. Okay. When we did it in the lab, mine came up earlier to 96 microseconds, someone else came up with 84. Another one was 90, 86, 87, 88. So there's some little bit of difference here. So I got 96 microseconds over 1,000 microseconds, which is, this is the time for one cycle. So this is big T, and little t. Okay. So I'm looking at the phase shift here. I've plotted the voltage from the source here, and it goes down, comes back up like that. Voltage at the cap, and there's from here and where it plots. So this comes up to 34.56 degrees. So I went over 34.56 degrees. I got a 30, 60, 90, so that makes this easy to find exactly where 34.56 degrees is. That's right there. And it's zero crossing going up as far from here. So this is behind or lagging a negative phase angle. Okay, and so this one starts 30 degrees away. It excuse me, peaks here, so this one peaks there, and this one goes down there, so this one the voltage across the cap goes down there, and so on. So if you do this 30, 60, 90, it makes it a lot easier to plot these waveforms. But I got a phase angle of 34.56 degrees and a voltage on this thing of about 5 volts. So if I was to plot this on my phasor diagram, I'd have a, let's see, earlier I came up with 5.08, but this time we came up with 5, and at 34.56 degrees. So that actually matches the calculated up here. This is what we calculated. Let's try this other one. Now, what we're going to have to do is change the circuit out. So we're going to do that and see how this one works out. Okay. Now, what I'm going to have to do here is change the circuit, because what I'm doing is measuring the voltage across the capacitor, and I need to measure the voltage across the resistor. So in order to do that, I have to take this off here, change these two around, put that in there, and that in there. Hopefully we don't have a, there we go. Okay, circuit voltage, right there. Now, I've got voltage across the resistor, and I need at least one of these. Okay, there's a voltage across the resistor on the yellow one, and the blue one has voltage of the circuit from here to here. Okay, so we'll go back up here. Oh, that's changed a little bit, hasn't it? Now, the yellow one is leading the blue one. So the blue one is the one we have as our static. It hasn't changed at all, but the yellow one did. We're measuring the voltage across the resistor. We're also, which happens to be in phase with the current through the resistor, current through the circuit. So, and you notice the current in the circuit is ahead of the voltage of the entire circuit. And this would also be ahead of the voltage on the capacitor. Okay, so a frequency hasn't changed. We're still at 1,000 milliseconds, 1,000 microseconds, and I need to find this phase angle here between the current in the circuit, or the voltage across the resistor, and the voltage of the circuit, okay, of the source. All right, so what I'm going to do here is use the source, or the scale, to stretch this out a bit. And what that has done is given me a, I'll use the cursors on these 2 points. Cursor, channel 1. Oh, where is it? That's where it crosses 0. About there. And I need to set the other one. Right here. Okay, so that says 154 microseconds from here to here. That's how long it takes. Remember, this doesn't work unless you make this waveform so that it is exactly the same distance here as here. Otherwise, you get some really strange readings from a phase shift. And you got to set the grounds at the same spot, because when you don't, you see what happens to the phase shift here? It gets shorter or it gets longer, which we don't want. So I'm going to set the grounds here at the same spot. Okay, so this says 154 microseconds. So we're going to back up here. What I had before was 156. Some students got 160, 164, 160, 164. Look like the 160s actually won. So I put 160 here over 1,000 microseconds times 360 degrees, and guess what angle it was? 57.6 degrees. The voltage on it was, what did we come up? Calculated was 3.192 volts on the scope. What's it say?
3.28.
Hang on a sec. There we go. On the scope, it says peak to peak for the yellow one, which is the voltage across the resistor, is 3.2 volts. Okay. And it came up with 3.2 volts, which actually earlier it came up with 3.3 at an angle of 57.6 degrees. Now we've got 57.6 degrees and 3.2 volts. So if I plot this thing, that 57 is almost 60, so I'm right here. So there's 30, 60, 90. It's going to peak right here. And you'll notice the interesting thing is it's peaking at the same time VC is going through 0 on a positive direction. That means that this is 90 degrees ahead of that. Okay, for this is what they call time domain. This is what they call phasor domain. Okay, you'll notice that there is a right angle between current in the circuit and voltage across the capacitor, and that's what we're actually showing here. Is that I got 57 degrees between here and here, but I've got 90 degrees between here and the voltage on the cap. So current and voltage are 90 out of phase. And so I've got these three waveforms. This peaks right there. And as this one peaks, that one's going through 0. As this one peaks down here, that one is going through 0. So voltage on the cap. So these here, these two here are 180, are they're 90 degrees out of phase with each other. Okay, and that's the lab for this week.